Hello, everyone, and welcome to this first session of Entanglement, Physics, Mind, and Worlds. I'm James B. Barbieri, Program Coordinator here at the PAR Center, and I will be your host for the next few weeks. So as a host, I'm here to help you. So any problems, feel free to let me know in the chat. As it's been almost 3 years now that we've been together, I'll brush very quickly on the guidelines. Just please remember to mute your microphone if you're not speaking. Turn on your camera. Feel free to use the chat as it's open. And of course, that this session is recorded for archival purposes. And for you all, you should all receive the link to the recordings in a few days. So as you may know, this is the first big online series of the PAR Center this year. And we thought to open with this topic of entanglement, as last year was a pretty big year for this topic, as the 2022 Nobel Prize in Physics went to Alain Aspect, John Clauser, Anton Zeilinger for the experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science, which brought back the mysterious notion of entanglement with renewed force, not only to the mainstream science, but also to everyday people, recapturing imagination as to the fundamental interconnected nature of the cosmos. In the spirit of the celebration, we start this year for the PAR Center with this online series entitled Entanglement, Physics, Mind, and Worlds, where we'll bring together world experts to discuss what entanglement entails from a theoretical perspective, along with the experiments that have confirmed spooky action at a distance and closed increasingly implausible loopholes that might provide another explanation. To begin this series, today we will be joined by the chair of this event, who brought all these wonderful experts who will be speaking with us in the coming weeks, Jonathan Allday. Jonathan has a PhD in elementary particle physics, and whilst doing his PhD, he spent some time at CERN in Geneva. He was co-opted onto a working party looking at the teaching of particle physics in schools and universities. The upshot was a new syllabus in particle physics and cosmology to be added to the UK A-level, which is 16 to 18-year-olds in physics qualifications. Jonathan wrote his first book, Quarks, Leptons, and the Big Bang, which was published in '98, and has also collaborated on a couple of textbooks and written his own books on quantum theory, general relativity, and the Apollo missions. Jonathan has worked as a physics teacher for 30 years in a variety of independent and boarding schools in the UK. He has been head of physics, head of science, and latterly an academic deputy head. He retired in 2000 and now runs a consulting company providing training and educational advice for schools. Now, while we understand that not everyone has a physics background here, Jonathan thought it would be a good idea to provide a grounding on the topic of entanglement, trying to avoid technical jargon, providing lots of space for questions for you all through this session entitled Entanglement for Amateurs. And with that, I'll pass it over to you, Jonathan. A very warm welcome.
Thank you very much, James. A whole group of world experts and me. Don't at all class myself within that group, but I guess what I'm going to try to do is be true to the physics, yet at the same time, hopefully try and pitch it in a way that more amateur approach, you'll be able to understand it and tee up what others are going to say over the course of the next few weeks. Let's start by just making sure that technology is on our side. I'm going to attempt to share my screen. So just bear with me for a second. Hopefully this should then share my screen, which you can see the presentation. James, can you confirm that's visible okay?
Looks good, Jonathan. Yeah.
Cool. And I hope people will forgive me. I'm going to switch my video off. I apologize for the implicit rudeness of doing that, but I've noticed over the last couple of days, my Wi-Fi at home has been a little bit glitchy, and I just want to make sure that there isn't too much bandwidth being taken up just trying to share the video bit. So here we go. Entanglement. When the left hand has some sort of implicit influence on the right. I'm going to divide this into two parts. The first part is going to be a hopefully soft touch, but nevertheless accurate look of what quantum theory is actually about. A little bit of the formality the formalism behind quantum theory, because that's going to be important in understanding the second part, where we're going to take a look at the actual experiments that have been done, the sorts of work that these trio of people have just received the Nobel Prize for. But also, it's entirely possible that some of the terminology, some of the ideas that I'm introducing during the course of this afternoon will actually be picked up and developed by the other speakers who come along over the next few weeks. So I think it's important and necessary to give you a little bit of an understanding, a little bit of an introduction to some of the jargon, some of the way in which quantum theory actually goes about its business. For a start, I'd like to just draw your attention to a couple of quotes. This is by Michael Morrison, who happens to have written one of my favorite textbooks on quantum theory, where he says that basically he's pointing out that quantum theory isn't some very strange version of classical mechanics, the old sort of Newtonian physics that we used to do. It's actually completely and totally different. And one of the challenges for students coming into this subject for the first time is actually deconstructing what they've already been trained in terms of the classical approach, so that they can sort of join quantum theory with a fresh start, because trying to bring too much of the classical ideas in just simply leads to confusion. And the other comes from someone who I had the very great privilege to get to know a little bit during his life, the very distinguished physicist and theologian John Polkinghorne. You know, I love this particular quote from him: "The average quantum mechanic is no more philosophical than the average motor mechanic." And what John is pointing out here, I think, is that for many working physicists, they just simply, the sort of vernacular phrase is shut up and calculate. They actually get on with the business of using quantum theory. They get on with the business of trying to do research, grant applications, moving science forwards, and perhaps don't spend too much time pondering what the quantum theory actually means, which can be a little bit of a shame, because there's a lot in there. And then, of course, finally, whenever you approach something like that, we must bear the maxim of Douglas Adams very much in mind over the next few slides. Okay, so the currency of quantum theory, the thing that you'll hear me chatter on about a lot, and any quantum theorist you'll hear discussing over beers in the pub, is something that we call the amplitude. The amplitude is something that an individual particle can have. You can have amplitudes for individual particles. You can have them for collections of particles. You can have them for complicated structures like atoms and molecules, etc. But the amplitude itself is a very odd kind of thing. It can't be directly observed or measured. In actual fact, in parentheses, because I'm not going to develop this point too much, it requires a form of mathematics that we call complex numbers. And I happen to believe that's a very, very significant and very pertinent point, but it's not one I'm going to stress. It does impact, however, on the fact that it cannot be directly observed or measured. We need to require a sort of mathematics that we don't come across in our daily lives. We can count 1, 2, 3 things, but complex numbers are somewhat different to that. The amplitude, or the state, the two terms are kind of interchangeable, contains all the information that's available about the thing that we're studying, be it an electron, a photon, an atom, etc. And if we square the amplitude, and I hope the technical experts will forgive me using the word square, we actually mean multiplying by the complex conjugate. If we take that amplitude and square it, then that tells us the probability of finding a particle at that point, wherever we're measuring. We have an amplitude to say the particle may turn up here. And if we square that amplitude, it tells us how likely it is to turn up there. Or indeed, the probability of manifesting any particular property that the particle might have. That's what the amplitude is doing for us. We can extract other information, not simply the position, etc. But the thing is that this strange amplitude is a kind of abstract mathematical pattern, and in certain circumstances does have kind of wave-like features associated with it. So when we set about doing our quantum mechanics, we write things like this. Okay, now hang on. Let's unpack what we've written here. This funny symbol on the left-hand side there is just saying the initial state, how we find the electron or the photon or whatever it is as it enters our experiment or as it enters the next stage of what's going to happen. This is the initial state, is symbolized by this funny looking bracket, and quite often we use the Greek letter psi and stick it in there. Now, what we've got on the right-hand side here in this particular case, two possible final states. So the result of our experiment, we had this initial state of the particle, but afterwards it might be either in state 1 or it might be in state 2. We don't know until we actually do the experiment. But these other two numbers here, these are the amplitudes. These are the things that tell us how likely it is that the particle will end up in state 1 and how likely it is that the particle will end up in state 2. So when we write something like this, we are saying that our initial state is broken down into a series of states, which is what the particle might become afterwards, multiplied by these numbers, which are these amplitudes, which tell us how likely it is that that change from the initial state into one of those individual states is going to happen. If you like, the amplitude is really where the physics lies. And we have various equations, Schrodinger's equations it's called, is the obvious example, that help us calculate the amplitudes in certain situations. So we go about plugging in everything we know about what's happening, and the amplitudes come out, hopefully. Now, it may well be that what we're trying to measure is something that is continuous, i.e. the position of an electron may not be just here or there, position 1 kind of here or position 2 kind of there. It could be a whole range of positions. It could turn up anywhere in a particular region. And again, the experts will forgive the slight notational clumsiness that I've used there. But the point is, rather than having just here or there, it could be a whole range of places, in which case these individual numbers here actually become like a spread of numbers. We might be measuring position, we might be measuring momentum. The amplitudes become a continuous spread of numbers. We say they're a function, if you understand, if you're familiar with that mathematical term. But really, all I'm trying to emphasize here is it's not just a set of 1, 2, 3 numbers. We've actually got now a whole range of different values of this amplitude, depending on exactly where it might be that the electron turns up. And indeed, this amplitude may depend on position. That's why that X is in there inside the brackets. It's telling us that the amplitude A depends on the position. And indeed, it may depend on time. So now we've got this spread of numbers rather than this individual collection of numbers. As we started off here, you know, 1 or 2, if it's a discrete situation, this guy turns into maybe that or maybe that. Could be a range of things. And it is this that's kind of sometimes referred to as the wave function. Sometimes physicists call about wave functions. Sometimes they talk about amplitudes. It's really kind of the same thing. Now, actually, while we're in here, just a little bit of historical interest, this funny bracket that I've using here, Dirac invented this, very great physicist named Dirac, and he referred to this as a ket. He invented this symbol and he called it a ket. It is from time to time necessary to use a slightly different sort of symbol, this one, and he called it a bra. Now, bear with me for a moment, because it is also necessary sometimes to combine these quantities, in which case you get this, which is what he referred to as a bracket or a bracket. This is the kind of thing that passes for humor amongst physicists. So, you know, we'll just say a little more about that and move on. Okay, so here I've tried to sort of give you a picture indicating the kind of thing that I'm talking about. We've got our particle, it may be an electron or whatever it is, in some initial state. A measurement is made. As a result of that measurement, we may find that some particular property we're trying to measure has a 1 value or 2 or 3 or 4, any set of these 5 values. These are the outcomes of our measurement. We would therefore write this. And again, it's the same idea as what I wrote before. We have an initial state, and after the measurement, we may find we're in state 1, we may find we're in state 2, we may find we're in state 3, in which case, if we're in state 1, the property is value 1. If we're in state 2, the property is value 2, etc. Now, what happens when we take the measurement is that this initial state randomly, and that's a very key point, randomly changes into one of the others. We can't ahead of time determine which one it's going to be. All we can say is our initial state may turn into state 1, in which case it has done that with probability, like I said, the amplitude squared. Or it may have turned into state 2 with probability, the amplitude 2 squared. Or it may have turned into 3 or 4 or 5, whichever. As a result of the measurement, this initial state, which we wrote as a series over the possible outcomes, changes in some strange way we don't entirely understand. It changes into one of the component states that we started off with, and that is how we get a measurement out the other way, at the other end. But again, very key point. We can't say ahead of time which one of these is actually going to happen. We can only say the different likelihoods, or hope to calculate the different likelihoods of which all of them will happen. It's often said, therefore, that quantum mechanics kind of describes things in terms of what they might become rather than what they are. You've seen I've just written the initial state there in terms of what might happen once I take the measurement. And I personally think that's a pretty fair characterization. Quantum mechanics, we talk about states, and we talk about states, we break them down into what they might become when the measurement happens or something like that. And it's possibly an important clue. You could say the state is the collection of amplitudes which tell us how likely it is to turn into other states. Maybe that's an important clue, that the way we should be thinking about reality is we should be thinking in terms of processes, not things. But again, I don't want to dwell too much upon that now. Maybe that's points that others will take up later. Maybe it's a point that will come up in conversations later. Coming back to this notion, though, that we have this initial state, which then changes into one of the others, and we don't know how it will change, and we don't know which one it will change into. This is referred to as the measurement problem. And it's one of the very big problems left in understanding how quantum mechanics and the world works. What is it that triggers this collapse of the state? Does the system have values before the measurement? I said, you know, as a result of the measurement, maybe the property is value 1, maybe it has value 2, maybe it has value 3. Did it have that value before we took the measurement? Or did the value come about? My own way of thinking about it is along these lines. The value came about as a result of taking that measurement. Some possibility was manifest. What causes that to happen, though? What takes a collection of possibilities and makes one actually manifest, makes one actual? This is what we refer to as the collapse of the state. That state that was a whole collection of possibilities to be something else. One of those is chosen, one of those actualizes. How does that come about? And that process, very important to understand. Take you back to a couple of slides before. I said we had equations that help us calculate what these amplitudes are. Those equations do not describe how that possibility becomes actual. That is something that sits outside of the equations. In a sense, it's something that sits outside of quantum mechanics as it is generally constructed. Although there are people, Roger Penrose there is one of them, who are working on theories where the equations of quantum theory are slightly modified in such a way as to include this possibility of how the collapse happens. But it's not part of what you might call the standard approach to quantum theory. It's an issue. Okay, huge block of text. Take a pause for a second. Entanglement. Here we go. Now, as far as I can tell, and I've done a little bit of research on this, this is where entanglement first enters the kind of terminology. Here is a quote from Erwin Schrödinger. And this was during a talk he gave to, I believe it was the Philosophical Society in Cambridge. And it's believed to be the first time that the word entanglement or entangled was used in the context of quantum theory. Let's pick apart what he's trying to say here to try and get some understanding of what entanglement actually is. Okay, so we start off with two systems. Maybe it's two electrons, maybe it's two atoms, whatever it is, whatever your system to choice is, we start off with two of them. And we know their states, what state they're actually in, and their respective representatives. Now, okay, I know people out there may not necessarily be mathematically fluent or mathematically comfortable, so forgive me when I scribble up something that looks a little bit like this. All I'm trying to say here is simply that we have amplitudes which describe one system, and we have amplitudes which describe another. So here we got this Greek letter psi again with the A underneath it. The A is to indicate I'm talking here about system A, whereas I've got another which is talking about system B. So we could have electron A, we could have electron B. And you'll notice that the amplitudes determine what's going on in system A only depend on the position of A, XA, where A happens to lie. The amplitude that's telling us what's going on with particle B only depends on the position of B. All I'm trying to indicate with that terminology. So Schrödinger's starting off with two systems. We know what's going on with them, and then we allow them to interact with one another in some fashion, collide, influence each other via forces, whatever. We allow them to interact between each other. But then, after we allow them to come together and interact for a period of time, then they separate again. Well, if that's the case, they can no longer be described in the same way as before. Those amplitudes that we had are no longer relevant. We have to now replace it with one amplitude, which depends on what's happening to both particles. As Schrödinger says, by endowing each of them with a representative of its own is no longer viable, no longer a correct description of what's going on. And he further says that this is not one of one, but rather the characteristic trait of quantum mechanics that enforces its entire departure from classical lines of thought. In other words, Schrödinger is saying here, this fact that when we allow the two systems to interact with one another, the description that we must use after that is no longer a description in terms of what's happening to one and what's happening to another separately. The description must be what's happening to them as a whole. That is the characteristic distinction between quantum mechanics and classical physics. Different quantum mechanics put their finger on a slightly different particularity to why quantum theory is different. You know, it's all our own particular taste to some regard, but certainly this is an extremely significant thing. And he goes on to say here, by the interaction, the two representatives have become entangled. In other words, what he's saying, and again, I'm trying to express that in this equation at the bottom here, that what we've now got something, this amplitude that we've got now depends on what's happening to both particles together, which is not the same as simply saying it's what's happening to one particle and it's one happening to another. The separate descriptions are no longer valid. And this joint description is not a simple combination of the two. It is something new. And there, as you can see, the word entanglement is being used. The entangled state is something new and not simply a product of the separate states that we had before. So here's Schrödinger introducing the idea of entanglement and what entanglement is actually all about. But the other thing, of course, that Schrödinger is famous for is that cat. And it's quite amazing to me how much Schrödinger's cat has entered the sort of zeitgeist of quantum theory, because it only appears in his written output once. He didn't stress too much about it, but lots of people have picked it up and talked about it. And here's the original quote again, where Schrödinger describes what's going on with this cat. And this is going to bring us back to entanglement once again. So you can see the quote starts by saying one can even set up quite ridiculous cases. Here we go with the ridiculous case. A cat is penned up in a steel chamber along with the following device, which must be secured against direct interference by the cat. In other words, the cat is not allowed to dismantle the device and save itself. We've got a Geiger counter in there, and perhaps with a tiny bit of a radioactive substance. Now, he goes on to say issues in detail about the radioactive substance, but the key thing here is that one of the atoms in the radioactive substance may decay or it may not. In other words, if we were going to describe this in the way that I've been using up to now, we would say that the state of the atom is a sum of possibly the outcome where it's decayed and possibly the outcome where it hasn't decayed. And you notice I'm using the same amplitude to both because Schrödinger actually says in his quote, with equal probability. So we're saying that our atom has a chance of decaying and also a chance of it's not decaying. And we'd write it in that fashion. But he goes on, he says, okay, right. Now, the mechanism is set up in such a way that if the atom actually does decay, it triggers a small flask of hydrocyanic acid. Clearly, Schrödinger was not a cat lover. And the idea is that if the atom has decayed, then the hydrocyanic acid flask will be broken. The acid, the gas will get into the room, the box rather, and the cat as a result will die. Now, if the cat is also describable in terms of a quantum state, and in one sense, that's a very big if, because there's a huge difference in scale. Obviously, a cat is much bigger than a radioactive atom. So we are making the assumption that the cat is describable by a quantum state. But on the other hand, the cat is presumably composed of no more than atoms and molecules, which of themselves are describable by a quantum state. So should not the cat itself be describable by a quantum state? Well, you know, one of the things that people like Zeilinger have got the Nobel Prize for was working on moving the quantum description to higher and higher scales. One of the latest experiments has been done is showing wave-like properties in things the size of about 1,000 atoms. Very large size now are all showing quantum properties. So we're not seeing yet an obvious line at which we can say bigger in this scale cannot be described in quantum terms. Below this scale it can. That scale is being pushed up and up and up in our experiments all the time. So it is entirely plausible at this stage, at least, that the cat would be describable by a quantum state. But the point is this: the quantum state of the cat becomes dependent upon what has happened to the atom. The cat is alive if the atom hasn't decayed. So what that means is the state, the overall state of the atom and the cat together is one that looks like this. The fact of the cat being dead is linked to the fact of the atom having decayed. The fact of the cat being alive is linked to the atom having not decayed. In other words, the state of the cat is entangled with the state of the atom. I cannot take these two systems, the cat and the atom, and separate them in such a way of what is happening to the cat is independent of what is happening to the atom. They've become intermingled. They become entangled. And so in a sense, this is Schrödinger showing that entanglement is something that we need to get a grip on, because in principle, we can get to quite ridiculous cases where the liveness or otherwise of a cat is entangled with what is going on with atoms. But it doesn't stop there. Because what happens to the scientist who is looking inside the box in order to determine whether or not the cat is alive? If we make the further assumption that that scientist is also describable by a quantum state, then when they look inside the box, and we know this is a scientist, by the way, because they're wearing a white coat. If we look inside the box, then they will either see a dead cat or they will see an alive cat. But until such time as one of those possibilities has been manifest, until such time that one of those possibilities that the atom has decayed or not has manifest, then we are forced to describe the state of the scientist entangled with the state of the cat, entangled with the state of the atom. Then, of course, the scientist's friend comes into the room and asks them what they have seen. And the state of, I heard him say the cat is dead, I heard him say the cat is alive, is then entangled with. When does it stop? Schrödinger used the phrase sinister in this context. He said this was of sinister importance, that the entanglement would just continue to spread until such time as something broke it, until such time as the wave function or the state, however you want to phrase it, until such time as that collapsed, in which case one thing, the atom having decayed or not, will be manifest, in which case all the other entangled things will follow from that. This, of course, leads us to a, I quite like it. Yeah, okay, it's possibly slightly morbid, but I quite like this. Someone looking inside Schrödinger's coffin at his funeral. You know, is Schrödinger's coffin entangled? Is it alive or dead? Okay, so in summary, what do we have? Two systems are entangled if their combined state cannot be separated out into individual states for the separate systems. In other words, there is now a whole which is describing both systems. They have merged into an overall whole, and our ability to describe them as separable systems has become blurred or lost. When the state, therefore, of one of them is collapsed as a result of a measurement, that has an influence on the state of the other. We have this wholeness, this overall state which describes both of them. If that state is collapsed into one of its possibilities because we have interacted with one of these two, then that will have an influence on what's going on with the other one. No matter, in principle, no matter how separated they are. And again, one of the things that our Nobel laureates have been doing is experimenting with these systems over greater and greater separations, so that interacting with one of them has an influence on another, even though they are separated by notable distance. Of course, we don't know that this entanglement, this influence, it extends indefinitely. That's obviously a subject which we must check by experimental test. But the quantum theory suggests, or at least the quantum theory in its standard form, suggests that the result of this entanglement, the influence of one upon the other, extends indefinitely. Okay. We must pause there for a second as far as entanglement is concerned. And now we need to move on, I'm afraid, and discuss another key feature of quantum mechanics. And the reason we need to discuss this is because this is the property or variations on this are the properties that we use in our experiments when we start to check out this entanglement. David Bohm was the original person, I think Basil will hopefully correct me if I'm wrong, to suggest, Bohm and Aronoff, to suggest that spin was the most convenient way in which to explore this. The original suggestions about some of the spookiness came from Einstein, Podolsky, and Rosen, and they were using something slightly more artificial. Spin is a very much more natural way to look at this. But what is spin? Well, it's a quantum mechanical property. The name spin itself is a rather unfortunate one, because it obviously conjures up pictures of something spinning like a top. If I say an electron has spin, it's very hard to avoid thinking in terms of a little tiny sphere spinning away like mad. But that description absolutely and utterly does not work. The name is unfortunate in that regard, but it was stuck with it. Why does it cause significant difficulties thinking this way? Well, some of those difficulties will come to light in a couple of slides' time. But just to give you an idea, if you did have a very, very tiny sphere of an electron, very tiny sphere of charge spinning, and if it would create the kind of magnetic field that we know the electron has, if it is just a little tiny sphere spinning away like mad, and that little current caused by that spin creates the magnetic field that we know the electron has, then the electron would have to be spinning at its edges faster than the speed of light, which we know can't happen. So whatever's going on here, it isn't spin in terms of a little sphere rotating like mad. Some ways it's actually quite a little bit easier to describe spin in terms of what it isn't rather than what it is, but I'm going to have a go. Now, the amount of spin, the amount of whatever this thing has, it's fixed. It's characteristic of the particle. An electron, we say, has spin half. Photons have spin 1. Other particles have spin of different types. We can't change that about the particle. If we were to change the electron's spin into something else, we'd have changed it into a different kind of particle. So that is, the spin itself is characteristic of the particle. But the direction of spin, and I've used the word direction in inverted commas here because, again, if you start using these terms, it's kind of making you think about a little object spinning like a top, and maybe the top's vertical, or maybe it's tilted over slightly, something like that. That kind of picture kind of works, kind of doesn't. We call it the spin component because we like to have terms that sound a bit posh. That is not fixed. That can take different values. And in fact, we first kind of discovered this with a very, very important and quite clever experiment carried out by a couple of physicists, Stern and Gerlach. Here's quite a nice diagram. There's a lot of detail I don't want you to look at here, really, but quite a nice diagram of how they did their experiment. Now, as I said earlier, that somehow or other, this spin of a charged particle, like an electron, electron's an electric charge, its quantum mechanical spin gives rise to a magnetic field. And that magnetic field, think of the electron as a little magnet, it will interact with another magnetic field, as a result of which there'll be a force, and that force will cause a deflection. Now, in this diagram here, we've actually got an experiment. There's the plaque that commemorates the actual experiment. It was done with a beam of silver atoms. They had this oven at the end here, a narrow slit to make sure that we don't get a whole splodge of atoms coming out. And we've got this beam passing between this very oddly shaped magnet, the north and south pole here, quite an odd shape to it. And the reason for that odd shape is it creates a magnetic field, which is good to kick the atom upwards or kick the atom downwards, depending on how its magnetic field is aligned. And what Stern and Gerlach were expecting to see when they did this, and they allowed the atoms to hit this photographic plate at the far end, although the beam was atoms, it was actually electrons in the atom, which is causing this to happen. They expected to see a continuous smear, You see, I've highlighted it on the diagram here. They expected their photographic plate to include this kind of smear where all the atoms were hitting, because the atom coming in, they expected the magnet to be orientated whichever way it was, and it would be kicked up a bit or kicked up less, and it would be this splodge. But they didn't get that. They got instead this very distinctive double patch. The electrons in the atom, the magnetic field, their spin wasn't orientated any way it wanted to be. It was either pointing, as we say, pointing upwards, or it was pointing downwards, and nothing in between. And so the atoms, due to the electrons, got kicked upwards, or they got kicked downwards. And that is a very, very strange property. The particular quantum property of spin, that it cannot point in any direction it wants. If it's an electron, it can spin one way, or it can spin the other way, but nowhere in between. So if I'm looking at the magnet kind of end on, you can see there's my particle beam, happens to be a beam of atoms maybe, and you can see that magnetic field between the two poles. We're saying that the electron's spin component, its direction, whatever this strange property is, can only have one of two distinct values, and that they are randomly manifest. We don't know ahead of time when the electron or the electron in the atom, when it enters this magnet, we don't know whether it's going to go up or we don't know whether it's going to go down. There's no way of telling. When I say up or down, etc., we are talking relative to the direction of the field. So if my magnet is vertical, then we say if the electron is spin up, it means that the atoms have been deflected upwards, and we'll join that top part of the splodge. If it's spin down, the electrons were deflected downwards and joined that bottom part of the splodge. And so we say there are two quantum directions that the spin can have: spin up or spin down. Now, this is going to be very important, because this is going to be what we're talking about right throughout when we come to the talk about the experimental checking on entanglement in the second part. So it's this idea that if we send the particle through this magnetic field, we are measuring the direction in which it is spinning. Again, we're using terms here which are not really appropriate, because the spin isn't like a top, and what we mean by direction is a little bit obscure here. What we mean is it will either be kicked upwards or it will be kicked downwards, and we can't tell ahead of time which it will be. On the other hand, if our magnetic field is horizontal like this, then that means that the beam going in, the electrons will either be kicked to the right, to the left, or they'll be kicked to the right. And I'm going to use +1 to mean up, or +1 to be left, or whichever. I'm always saying if it's +1, and I've got it the wrong way round in the text here, so forgive me, got my left and my right's mucked up. We're saying that if it gets kicked towards the magnetic field, it's 1. If it gets kicked towards the South Pole, it's -1. And of course, when we say north and south, I mean not the direction on the Earth. I obviously mean the direction of the magnetic field. I'm talking in terms of charged particles like electrons and their magnetic fields here. Actually, the experiments that have been done are in terms of photons, which don't have a charge and so don't interact with the magnetic field, but there are equivalent ways of doing the experiments. I'm going to talk as if the experiments were done with these magnetic fields. They're actually done with a different technology, but I think it's easier to stick with this explanation. So here we are back at our states. Deep breath, don't panic. Again, we're describing the atom or the charged particle going into the magnet. We say it has an initial state, and that initial state is composed of the possibility that it might be spin up, which is that state, or the possibility that it might be spin down, which is that state, and that's the amplitude that the spin up will be manifest, and that's the amplitude that the spin down will be manifest. It's 1 over the square root of 2, because if I square it, that will give me a half, and that's telling me it's equally like half a half, it's equally likely to be either. We might use, it might be in different situations that it isn't 50-50 chance, in which case the two amplitudes wouldn't be quite the same. But again, we're working on that basis. And we sometimes write it like that, which is no more than just gathering the half outside the bracket. But again, it's this idea that we're writing the initial state in terms of the possibilities that might manifest themselves. So let's imagine we do an experiment in which we create a particle and it zooms off to the right, to the left. Well, it might be spin up, it might be spin down. And so I describe its state like that. Shaded, that bit there is describing that particle zooming off to the left there. I've used the subscript A to indicate that particle A might be spin up or it might be spin down. If I separately create another particle and it zooms off to the right, then I would describe its state as being possibly spin up and possibly spin down. And I've used B underneath to indicate that we're talking about particle B. Now, these two particles kind of don't know about each other. I've created them separately. So really and truly, that's not a particularly interesting situation. What we've got here is describable in terms of the separate features of what are going on for each particle. But, and this is what the experiments do, instead, if we kind of create both particles at the same time, and in particular, if we say that the total spin of the system, and that's a constraint we put on it when we do the creation, as it were, the total spin of the system is 0, then I have to use this as a state instead. And this is rather different because you can see now that the A's and B's are mixed together. If the total spin has to be 0, then if A manifests as up, that means that B must be down. Whereas on the other hand, if A manifests as down, that means that B must manifest as up. And so this state that we've created here is an entangled state. We cannot separately describe what is happening to A without including what is happening to B. The two are entangled together. And that is the particular type of state that we use as the linchpin, the crux, the starting point of all these experiments. So, important questions. If we were to isolate, remember we've got these electrons, we've kicked some of them upwards, we've kicked some of them downwards. Let's say we just take the ones that we've kicked upwards. So we know that they're in a state of being spin up. There they are, symbolized by that, symbolized by that arrow. But what would happen if we let them go through a horizontal magnet? So we've separated out the electrons. We know these electrons are spin up, but we're now going to torture them by passing them through a left-right magnet. What happens? Well, what happens is that some of them come out of that magnet left and some of them come out of that magnet right. 50% of them come out left, 50% of them come out right. And we can't tell ahead of time which is going to be the case. Same thing would happen if we took the electrons that have been deflected downwards so that they were spin down. If we pass them through a horizontal magnet, half of them would go one way, half of them would go the other, and we couldn't tell. If we send through a magnet at another angle, so not left, not sort of horizontal, but at some tilted angle, then some of them will come out up and some of them will come up down along the magnet's angle, but the fraction won't be 50-50. It will depend on the angle of the magnet. Indeed, the more nearly the magnet is vertical, the more likely it is to be spin up and the less likely it is to be spin down along this funny different angle. And again, this is one of the features of the experiments that we'll come up with, because we're going to send the two particles in different directions. We're going to measure one at a certain angle, and that's going to collapse the state for both of them. But then we're going to measure the other at a different angle and see what happens as a result. But I've been chattering along possibly for slightly too long. I think this is a good moment, James, for us to have our quick coffee break, let people's brains come out of feverishness, and then we'll take a look at the experiments that have been done to actually check out entanglement and its consequences. Basil, I saw you nodded when I said it was David Bohm who suggested the use of spin. But yes. I think I went on to say it was Bohm and Aronoff, but it was just Bohm, wasn't it?
It was just Bohm, and I've just checked it up. It's chapter 32 of Bohm's book, Quantum Theory. That was his book.
Oh, was it? Was that? I did wonder. Was it actually in his textbook? Which it's in
the textbook. Yeah, it's certainly in the textbook. Whether that's the first time it appeared or not, I couldn't tell you, not offhand. But it's certainly in his textbook. And it was long before Aronoff came on the scene, actually.
Okay. It's a book I picked up when I was an undergraduate, actually, and absolutely adored that book.
Yeah, well, did you realize that he actually said hidden variables were not possible in that chapter 22?
Yes, I remember that. Yeah.
And then he goes and publishes a paper in 52 saying hidden variables.
Yes. Yeah, well, but I gather you'll know much more than me, but I gather he kind of regretted referring to that as hidden variables in a way.
Well, that's my interpretation of it. We have discovered an earlier draft. Drise in France discovered in Du Bois' filing cabinet or some box or other a draft of that 52 paper of Bohm's, and it's called A Causal and Continuous Description of Quantum Processes.
Oh, right.
Which is very interesting. I wish he'd stuck with that label, that title.
Well, because I think, is it possible if he hadn't called it a hidden variable theory, it might have got more traction in the community?
That is my guess, but of course it's counterfactual.
Yeah, no, exactly. Yeah, I get that. Yeah.
But I certainly think, because there was such a heated debate when I was working. See, I began working with him in 1960, 62, I think it was, which is going back quite a long time.
I won't tell you how old I was.
And it was the hidden variables there that was really causing a lot of anger. I remember going to meetings with him. You know, I just got my PhD and was wondering what the hell was going on in academia. And I'd go along with him, and there would be shouting matches and goodness knows what else whenever the word hidden variables came up. It really was emotionally charged.
Amazing.
Part of the problem wasn't it, Basil, that I mean, von Neumann had laid down the law in people's minds at that date, that there could be no.
Yeah, but then you see von Neumann later on in 36 then said, "Oh, I'm sorry," writing a letter to Birkhoff, you remember, Mike.
Yes, indeed.
I'm afraid I'm going to commit a heresy.
I no longer believe in Hilbert space. Yeah. But very, very few people knew about that letter, and the Orthodox, but certainly the Orthodox received view in 61, 62, the period you're talking about, was very much that von Neumann had laid the whole issue of variables theories to rest, and there was a no-go theorem. Therefore, these people must just be ignoramuses or whatever. I mean, I'm not suggesting, not endorsing that at all. I'm just saying I think sociologically that was why there was that kind of a reaction. But can I just ask one quick question about the book that David's just been talking about? The textbook, David's original textbook of 1951, I think, wasn't it? But it was just before the causal interpretation paper. The whole point about that was that it was deliberately intended to be a presentation of the kind of strict Copenhagen orthodoxy.
Yeah.
Well, shall I tell you this? Have we got time for me to tell you the story of how that
I
came
don't know.
about?
Better ask Eleanor. Sorry.
You've got 5 minutes, Basil. Can
Okay.
you do it in 5?
Well, what happened? Well, just shut me up when everybody else is back.
I'll try.
No, what David
Good
said,
luck. Good luck with that, Eleanor. Sorry.
what David said to me was that he was teaching a course on introductory quantum mechanics at Princeton.
Yeah, that's what I understood.
And what happened was he got to the end of the course and he said, oh, I don't know. He said, I don't think I understand this. So he then decided the best way to understand it is to write a book. So unlike me, he immediately wrote the book explaining the orthodox. And then he said, you know, right through to chapter 22 with the hidden variable argument in there. And then he said, when I finished the book, I suddenly realized it's not right. There's something wrong with what I've written. And that's what got him talking to Einstein, because Einstein was in the Advanced Institute at Princeton.
Yeah, cool.
And that's where they started discussing. And of course, people blame Einstein for corrupting David Bohm. I've actually had I think it was Murray Gell-Mann was the name that was mentioned. This is all hearsay, so I'm not quite sure how factual it is. And whereas in fact, David said, no, Einstein did not influence me. I went there telling him how to do it. So, I mean, the great thing about David Bohm, he didn't lack courage, intellectual courage. But that's the story.
Very interesting.
Basil, can I just say hello while you're there? It's Bernard here.
Oh, hello, Bernard. How
Hi.
are you?
Oddly enough, I've just come back from Oslo. And when I was there, I met someone called Henrik Schude, who you may know, and he had a copy of David Bohm's 51 textbook, which oddly enough I never had. So he gave it to me. So I just came back with his textbook just a few days ago.
It's an extremely interesting book because it discusses the meaning that rather than just the formalism, trying to give an explanation of why things were working the way they were working.
Yeah,
That's what attracted me to it as an undergraduate. It was the ratio of words to equations was tipped heavily in favor of words.
That's right. Nowadays, you wouldn't get away with it. Anyway, that's very interesting.
and hi, Jonathan.
Hello, Bernard. How are you?
Fine indeed. And it's such a clear presentation. Thank you so much.
It saved me a lot of work.
Yep.
That's very flattering.
But I would expect that because of your great book on the subject.
Very kind.
I have to say, Jonathan, I think that was absolutely the clearest presentation of the whole issue of entanglement and well, an introductory talk on quantum mechanics I have ever heard anybody give. I mean that quite seriously.
Well, that's extremely flattering and very, very kind of you. I just hope to God it doesn't go rapidly downhill in part 2.
It's interesting, Jonathan, one point you make before the others come back about you can't interpret it as spin because the speed of light would, the speed of the spin would exceed the speed of light. I've never been completely convinced by that because it's true, of course, for the classical electron. But if you take the particle radius to be the quantum wavelength, the rotation speed is exactly the speed of light, at least if it's spin 1. And so I've never, of course, it's true. It's not literally a spin, but in so many ways it is like an actual spin. And I've never been completely convinced by that argument because, after all, in quantum theory, you're anyway, in some sense, transcending the speed of light limit in other senses.
Well, quite. No, quite. I fear I rather glibly quoted that argument in my book without actually doing the calculation.
Well, I think it's an argument people often make, but I've never found it completely convincing. To me, it's an interesting coincidence that the quantum wavelength of a mass gives you the speed of light if it's spinning with, if it has h bar as its angular momentum.
Yeah. Yeah.
Well, thank you, everyone. This has been a really beautiful break. It felt a bit like the coffee breaks when we're in person at the party center, where we hear all these different ideas and exchange and see friendly faces again. So thank you, Bernard, Mike, and Matt.
And also, of course, James, I have to say hello to you and Eleanor as well.
Of course, always great to see you, Bernard. Hi. So if everyone's caffeinated and ready to go again, are we all happy to start? Great. Over to you then, Jonathan.
Whether you're happy or not, we're going to. Okay, so what I'd like to do in part 2 is take a look at the basics of these experiments that have been done. Again, I hope the experts will forgive me in that I'm taking a few liberties with the actual technical details of how these experiments work. There's been some absolutely outstanding experimental work done here, and I'm glossing over a lot of the details. But I think that's inevitable if we want to get to the meat of the physics of what's going on. Okay, so there are certain properties, charge, mass, and total spin, for example. And you might refer to those as system properties. In other words, they tell us what system we're dealing with. An electron has a certain charge, it has a certain mass, it has a certain total spin. If we know those properties, then we know we're dealing with an electron. And those are fixed properties. Whereas the electron might have a position, it might have an energy, a momentum, a spin component. Those are properties which tell us which state it is in. The electron can be in a whole range of different states, what position it's got, what energy it's got, what momentum it's got. These are state properties. And these properties are not fixed. Whereas the system properties are, the state properties are these properties which are governed by the amplitudes. Different values of these properties will manifest themselves in a random way. Now, of course, as we well know, Einstein didn't like this aspect of quantum theory. His own personal philosophy was very much a deterministic philosophy, and he didn't feel that quantum mechanics could be the last word on the subject because, as often phrased, often quoted, he didn't believe that God played dice with the universe. In other words, generally, if we talk about probabilities, it's because we don't know enough about the system, or the system's too complicated for us to be able to actually calculate what's going on. It's very difficult to keep track of the billions of particles of the gas in this room. And so we use averages, we use statistics, we use probabilities. That's not saying that the particles don't have these positions and properties. It's just saying we don't know enough about them. That's one use of probabilities and statistics. But quantum mechanics isn't like that. Quantum mechanics is saying that these possibilities manifest themselves because it is inherently random. Well, Einstein didn't believe this, didn't countenance this. He was one that was suggesting that perhaps quantum mechanics wasn't complete. Perhaps there was some hidden properties, some properties we did not yet know about. And that if we did know about these properties, we would be able to calculate and predict exactly what outcome is going to come from a measurement. He had no clue, and the physicists generally don't have any clue what these hidden properties might be. We just speculate that they might be there. And if they are, maybe all this randomness would go away if we could find these hidden properties, measure them, get values, and then we could do proper calculations in that phrase. Well, one person that picked up this idea was John Bell. And John Bell was pondering, in fact, he was prompted by much of the work of David Bohm, it actually happens to be, I only discovered comparatively recently. He was pondering the possibilities of hidden variables. Some physics that we don't currently know actually determines the outcomes. And this physics is a hidden quantity or hidden variable or variables. Now, Bell wasn't setting out to actually create a theory. using particular hidden variables or anything like that. He set out to wonder, in general, could any form of hidden variable theory actually reproduce the results of quantum mechanics? Not a particular theory, but a theory, hidden variable theory in general. Would it be possible to reproduce the results of quantum mechanics that way? And the sort of experiment he envisaged, the sort of experiment we're going to be discussing at length, is this notion that you start off with a pair of particles in an entangled state, that they separate, and that one reaches a detector, which we're going to call Alice for no readily apparent reason, and the other zooms off in the other direction to a detector called Bob, again for no readily apparent reason. But underneath this, there is some hidden variable. I'm going to call it L, actually thinking about it also for no readily apparent reason, other than it's usually lambda, and I didn't want to use a Greek letter, I think. This hidden variable L exists, which will in some sense determine what we find at Alice and determine what we find at Bob. Let's look at it in a little bit more detail. So we've got these two detectors, which we're going to call Alice and Bob, and they're going to measure the spin component along some angle. Remember I said this was going to be how we were going to look at things. So the particle reaches Alice and we measure its spin component along some angle that we choose. You may have noticed that Bob is a little bit further away than Alice. So the particle on the left-hand side is going to reach Alice first, and then a bit later, the other part of the pair, is going to reach Bob. Now, Alice and Bob both have their magnets set at particular angles, and the angles can be adjusted. Ideally, and this is some of the developments that came as the experiments got better and better, adjusted while the particles are in flight. So if Alice and Bob have their certain angles set, we create the particles in their entangled state, and they fly off towards Alice and Bob. We trick them by changing the angles before they arrive. So if in some way there's some conspiracy between the detectors and the creation of the particles, which is kind of tipping the particles off as to which angles Alice and Bob are set at, then we fool that by changing the angles while the particles are in flight. And also, as I said, we measure at Alice's end before the particle reaches Bob. Now, going back to with the way in which we've created this state, it's a spin zero state. The total spin must be zero. So if Alice and Bob measure along the same angle, let's say for convenience, they're both vertical, then if Alice, the particle that reaches Alice, manifests as +1, we know before it arrives at Bob, the particle there must be -1. If Alice, the particle manifests at Alice at -1, we know while the particle is still in flight and arriving at Bob, it must be +1. And so we can predict what Bob is going to find when the particle arrives there. On the other hand, if the Alice and Bob angles are 90 degrees apart, remember I covered that case, then if Alice manifests +1, we don't know what's going to happen at Bob. We know Bob is going to be -1 vertically, but Bob isn't measuring vertical. He's measuring horizontal. So it's going to come out ±1 in a random pattern. Equally, if Alice manifests at -1, we know Bob is manifesting as +1 vertically, but we're not measuring vertically, we're measuring horizontally. So the outcome at Bob again is unpredictable. It'll just be +1 or -1 at random. Now, if Alice and Bob are actually at some intermediate angle apart, then if Alice measures +1 and if Alice measures -1, Bob will measure +1 and Bob will measure -1, but the results will be correlated. It won't be random. There'll be a greater tendency to get +1 if Bob's angle happens to be nearly the same as Alice's angle, etc. There'll be a correlation. but that correlation will depend on the angles. And that's where it gets tricky. Okay, sorry, a little bit of math here, but it just makes the terminology a bit easier. But it makes it easier for me. So we've got this hidden variable, L. We don't know what it is. We're just supposing it might exist. Over at Alice, we've got some physics. We don't know what it is. We've got some physics, which I'm sort of imagining as this thing A. And what happens is determined by the value of the hidden variable. L is in there, but the little a, that's the angle at which Alice is measuring. So, important things to note. If this hidden variable is actually there and it's actually influencing what's going on, then it is set to whatever value it has when the particles are prepared. At the moment the particles are prepared, this hidden variable gets its value. Also, as I phrase it, locality is baked in here. Because what we're saying is the result that we get at Alice, it only depends on this variable value, L, and it only depends on the angle A, which Alice is using. At Bob's end, the result only depends on L and at Bob's angle. And that's what I mean by locality in this context. What happens at Alice only depends on Alice's angle. What happens at Bob only depends on Bob's angle. And there's no way they know what the other setting is. So B is the physics that's going on at Bob. It depends on the angle setting of Bob, and it depends on the value of the hidden property, which somehow or other got created and fixed when the interaction created the particles took place. So we've got two functions, if you like, A and B. We've also got some probability, which sets how the particular value might come about. All I'm saying here is Bell's model here is very, very general. We've not said what this property is. We've not said what the physics is going on at Alice or Bob. This is a very, very broad and general thing. He is not trying to say here is a particular hidden variable theory. He's just trying to say what will happen to all possible hidden variable theories of this type. Now, if the two angles happen to be equal, then what we might say is that this function A is going to give us the value +1 or -1. And if it gives us +1, we know that Bob's got to get -1. In other words, if Alice manifests up, we know that Bob manifests down. And it's quite easy to imagine how we could create two functions, two bits of physics at A and B that are going to do that, that if one is up, the other must be down. That's easy. We can do that. If Alice and Bob are 90 degrees apart, so one's measuring vertical, the other's measuring horizontal, then we know if Alice gets +1, then Bob might get +1 or he might get -1 randomly. If Alice gets -1, then Bob might get +1 and that's, again, that's easy. We're saying that A and B are disconnected from one another entirely. The problem lies is if the two angles aren't the same and they're not 90 degrees apart, in which case what happens at Alice and what happens at Bob are correlated, but furthermore they're correlated on a way that depends on the two angles. And actually building a hidden variable theory that will do that, that's tricky. The two angles are the same, the results are opposite. The two angles are 90 degrees apart, the results are random. At any other two angles, the results are correlated with one another. Now, what Bell wondered was, how correlated can they actually be? Is there a limit to the extent to which these two sets of results can actually have a pattern which is correlated one to the other? And in fact, does quantum theory break that limit? Because if there is some limit to how well correlated the results of A and B can be, given these local constraints that I've said, and quantum theory breaks that limit, then quantum theory cannot be reproduced by a hidden variable theory. That's what Bell is driving at. Is there a limit to the sorts of correlations that a hidden variable theory can create? If there is, And it turns out there is. Does quantum theory break that limit? But then there's, of course, a third question, because we're saying on the one hand, here's a hidden variable theory, and here's quantum theory. But how does nature actually behave? It would be very interesting if the hidden variable theory couldn't reproduce quantum theory, but nature actually behaved like a hidden variable theory. That would tell us that quantum theory was actually wrong. So there's a third factor in here. How does nature actually behave? Okay, so how do we do these experiments? Right, what the experiments do is kind of like this. You run the experiment for a period of time. A and B, Alice and Bob have got their angles set. And we've got these counts. N++ is simply the number of times that Alice got spin up and Bob got spin up on their different angles. N minus minus, number of times that they both got minus, minus plus, Alice gets -1, Bob gets +1, plus minus, Alice gets 1, Bob gets -1. So we just let the experiment run, tick away for itself, and we simply count all these different counts and let the computer count them up how many times this happens. Now, if A equals B, in other words, if they're both on the same angle, we know that N++ must be 0. You know, if they're both measuring vertically and Alice gets +1, we know that Bob can't get +1, he must get -1. So we know in those instances that things like N++ and N-, will be 0. What we're interested in is the counts that happen in the other possibilities. Now, what the experimentalists do is they actually calculate this thing. And again, forgive me, but I do think it's useful to have a little idea of what's going on. I'll break it down for you. Let the experiment run for a long period of time, so you get these counts. So I've got the count of plus plus, the count of minus minus, the count of minus plus, and the count of plus minus. Now, plus plus means that Bob was +1 and Alice was +1. So I take +1, multiply it by that. Minus minus means Alice was minus, Bob was minus, so I take minus minus, multiply it by that. You get the idea. Basically, I take the spin value for each one and I multiply it by the number and I add them all up. And this kind of gives us, I divide by the total number, this kind of gives us an average. It's an average when I take the number of times they both got spin up times plus plus, number of times they both got spin down, minus minus, minus plus, plus minus. I kind of average them all out. And that's what this E number is. But then what you do is you say, okay, well, we're going to say Alice and Bob can be one of two different angles, A or A dashed and B or B dashed. So we've got two possible angles at Alice and two possible angles at Bob. And we let the experiment run with all the different possible combinations. So we run for a while with Alice set to A and Bob set to B. We run for a while with Alice set to A and Bob set to B dash. We run for a while with Alice set to A dash and Bob set. You get the idea. And we accumulate all these different counts for all the different combinations of the four angles. Ideally, changing the angles while the particles are in flight. This gives us four different counts, then four different averages. The average when A and B, the average when A and B dashed, the average when A dashed and B, and the average with A dashed and B dashed. So we run these experiments and we get these four different kind of averages. And then what we do, oh, by the way, we should say, if each detector is simply doing its own thing, then each of these would be 0. If there is some correlation going on, in other words, what's happening at Alice seems to be influencing what's happening with Bob, then these won't be 0. Oh, by the way, also, why do we only pick 2 angles? Wouldn't it be better to have 3, 4 angles? Well, give them a chance. It's hard enough to do the experiment like this. Okay, so again, what they then do is they combine them together to give this overall parameter called S. The exact details of what the combination is isn't really crucial, but the idea is you sit down, you get these separate runs of the experiment, and then you combine them together in this fashion. What is it? Well, it's an experimental way to measure how correlated what goes on at Alice with what goes on at Bob. Yeah, but what is it? It's going to tell us how connected Alice and Bob's results are. If we can measure this, determine the experimental, that's why my S has got little subscript E. If we can determine the experimental value for this, it tells us how correlated Alice and Bob are. Yeah, but what is it? Well, it's actually called the Clauser, Horn, Chimney, and Holt parameter. And notice one of the Nobel Prize laureates' name in there. So, right, the number S, this number S is something we have to find out by experiment. We just have to do the experiment and find out what nature is doing. Find out how correlated Alice and Bob's measurements are in nature. But Bell was able to calculate, and don't worry, I'm not going to show you the details or even begin to speculate on the details of that calculation. But Bell was able to show with some very, very clever and simple maths where there was a maximum limit in a hidden variable theory, a variable theory set up the way he'd set it up. And he found that value had to be less than or equal to 2. If there is a hidden variable, a local hidden variable theory at work, then when we do these experiments, we will find that the correlations that we get cannot be, the value of this number cannot be greater than 2. It's kind of telling you the extent to which it could happen by accident in a hidden variable theory. But you can also calculate the quantum prediction. What does quantum theory predict that this value will be? And if you do that, you've got to, actually, it's better to do a particularly adroit choice of angles. And if you set those angles like that, and it turns out that the quantum prediction is twice root 2. In other words, clearly greater than 2. Quantum theory would violate the hidden variable version. But of course, what we need to do is find out what nature is actually doing. And this is where a whole series of experiments started to develop. Clauser started some of the initial work, but Alain Aspect was the first persons, or his group was the first people to really, as the technology and techniques developed, they came on board with the first robust test of this. Now, what they got as their measure, they had to make some corrections for efficiencies and lens apertures, that sort of thing. Their value of what they measured for these correlations, 2.697 plus or minus 0.015. What does that mean in human speak? It means that they're saying that the value of S that nature gives us is somewhere between 2.7 and 2.68, 2.712 and 2.682. Clearly greater than 2. Clearly greater than the extent to which a hidden variable, a local hidden variable theory could actually generate these correlations. The correlations whereby Alice's physics depends only on what's happening there, Bob's physics depends only on what's happening there. The extent to which the correlations could be have to be less than 2. Nature is more than that. The corrected prediction for quantum theory, taking account of the efficiencies in the experiment that it actually did, 2.70. So not only is this experiment telling us that nature violates the constraints of a local hidden variable theory, it's also telling us that nature agrees with quantum theory. So what's the punchline? We measure a particle spin component by Alice. You get the result +1. Some time later, we measure the spin components at a different angle by Bob. We're more or less likely to get +1 depending on the difference in the angles. How does Bob and Bob's particle know the angle that was set at Alice's end? How does it know the result at Alice's end? In particular, if there was no time for any signal to get from Alice to Bob. Nature appears to be correlating these two results, but nature also appears, at least at the explicate level, if I can use that term, not to be giving us any mechanism by which this can happen. We started off with this spin state. There it is, our entangled spin state. If Alice gets +1, Bob must get -1. If Alice gets -1, Bob must get +1 along the same angle. We're not measuring that, but I'm just saying what the state is telling us. And that 1/√2 there is just to make sure that the probabilities add up to 1. It's an entangled state. It cannot be factorized into product states for each particle. After Alice's measurement, one of these possibilities manifests. So Bob gets either the +1 -1 bit, or he gets the -1 +1 bit. The result that he measures, because his angle is different, will be preferenced towards +1 or -1, depending on which angle he chooses to measure. But the key point is the amplitude has collapsed everywhere at the moment that Alice's measurement has been made. Now, there are some very, very general assumptions going on here. And here we got a quote from Aspect himself. There are 2 hypotheses that are necessary to obtain Bell's inequalities, this number S that I showed you, the inequality being it has to be less than or equal to 2 for it to be a hidden variable theory. One assumption is that the distant correlations can be created by having this hidden variable L. The other assumption is locality. Those are the only 2 things that go into Bell's proof. Nature doesn't respect these proof. So one of these is dead. Either there is no such thing as a hidden variable theory, or if there is a hidden variable theory, it must violate locality in some very, very strange fashion. And this is why we sometimes say, or sometimes hear said, that quantum mechanics conflicts with local realism. So I'm trying to pick up the pace a little bit here. Basically, we're saying that this proof is very, very general. But there are some possible loopholes. There's what's called the detection loophole. Maybe you're missing some significant particles. There's the locality loophole. Maybe some other influence is traveling from Alice to Bob. There's the memory loophole. Maybe what's going on in the environment, because Alice and Bob are sitting in their environment for long periods of time, maybe something's going on there. And most significantly, most interestingly, there's the free choice loophole. More about that. Let's talk about these loopholes one by one. Detection loophole. Basically, your detectors can't be 100% efficient. Sometimes they miss particles. And you can compensate for that. That's what, the parameter was adjusted to account for the fact that maybe you miss a few particles. Your detectors can't be 100% efficient. But if you take a conspiracy view, you could say, all right, you're missing some particles. Maybe if you included them, they are of a different statistical nature. And maybe if you included the missing results, that would alter the overall and it would bring it back in line with the upper value. You're saying that for some reason or other, the particles that you're seeing are violating it, but there are more particles that you're missing which don't violate it. And if you included them as well, then all will be well. It's a bit paranoid. Well, it's a general hypothesis in physics that you don't miss anything that's radically different to what you've got. But in particular, this loophole is now closed. I mean, detector efficiency, when we first started doing these experiments, was only about 20 or 30%. It's now up to 93%. So it stretches credulity completely to suggest that the 7% missing are of a statistical nature that's going to change the outcome of the result. It's just not going to happen. The locality loophole, we need a balance between the speed at which the particles can travel and get to Alice and Bob, the distance between the detectors, and the rate at which they can take their measurements and the rate at which they can change their angles. We need to make sure that Alice lies outside the Bob lies, I've got it the wrong way around, sorry. The Bob lies outside the causal radius at A. In other words, that things are happening too quick and too far apart for any message to get from Alice to Bob. That means there's no classical way that the events at A can influence B. Well, as technology has improved, Alice and Bob have got further and further apart, and there are no significant particle loss during the flight. Again, we declare that loophole closed. We've got further than this now, but the first experiments where Alice and Bob separated by 18 kilometers effectively closed that loophole. There's no way that an information could get from Alice to Bob in time to influence what's going on. The memory loophole, again, the idea here is if A and B remain in fixed positions, there may be some conditions local to those detectors could have an influence on the successive measurements. Maybe the physical parameters of the environment are changing in some way that is influencing what's going on. You can, however, show that if these successive measurements, these successive angle changes are happening randomly, it shouldn't really have any effect on the outcome. You're randomizing by the changes in angles. The first experiment that effectively closed the detection, the locality, and the memory loophole all happened in 2015. So we're now declaring those three loopholes closed. Which leaves the free choice loophole. This is the most interesting one for me. The assumption that we've made is that our ability to choose, or our ability to set up the technology to choose which angles are going to happen, is uninfluenced. In particular, whatever value of this hidden variable is set at the moment at which it was created, it has no influence on our ability to choose the detector settings. That's a fundamental assumption that we've made. And it's a very plausible assumption. But physics paranoia really coming to the fore here. What if some event earlier in history influenced both the detector settings and the value of the hidden variable? Maybe some business in the past has influenced these things, and our ability to choose what the angles are, apparently randomly, is not in fact a random choice. It's influenced what's going on in the past. And hence, the violation is coming about. Well, you might say we could overcome this loophole by using some sort of quantum system. Remember, quantum systems are random, which influences and sets the detector. But that's not going to work. Even if we use a quantum system to generate random numbers to determine the detector settings, it might be that whatever this thing going on in history also influences these systems. We're getting really paranoid now, but it is a loophole that needs to be closed. And it's being closed. Because what they have done, this is a gorgeous experiment, is they've set it up so that there are two distant quasars. Quasars are extremely powerful active galaxies, we think, and we've taken the light from these quasars, and we're using the photons in the light from these quasars. We're using that to set the value of A and B. Now, given how far apart these quasars actually are across the universe, and given how far away they are from us, the only possibility is that some event further back in time is mysteriously influencing these separate quasars, influencing their light. Their light is then affecting the values of A and B. But whatever that event might be, it had to have happened around about 8 billion years ago, which stretches implausibility. Because we're using these two separated quasars across the universe, the light from them helps us set the values of A and B. Then if there is some event which influenced the quasars, influenced their light, which now influences our choices, that event had to have happened 8 billion years ago. Doesn't seem plausible. So, in other words, all the loopholes that might get out of this have effectively been closed. There is no wiggle room. Nature, we have measured. She agrees with quantum theory. She does not agree with the upper limit of these correlations that you could get from any local hidden variable theory. One hesitates to say that there's something worse coming, but I'll just mention it briefly. Bell's inequalities. This number has shown us that any hidden variable theory must be non-local. If there is to be a hidden variable theory, it has to be non-local. It has to mediate influences that effectively break relativity. There's also something called the Koch-and-Specker theorem. Let's say very little about that. But that tells us that any hidden variable theory must also be contextual. Very quick. Let's say we got 5 physical properties, 1, 2, 3, 4, 5, and we choose to measure them in clusters. So let's say we set up an experiment to measure 1, 2, and 3, or we set up an experiment to measure 2, 3, and 4, or we set up an experiment to measure 1, 5, and 2, or 4, 5, and 2. There's a hidden variable that's actually determining the values. Well, the Koch-and-Specker theorem actually tells us that that variable cannot have the same value in all of these situations. It's just a no-go. It cannot do it. It cannot be done. And so the value of property 2, which is in common there, the value of property 2 that we get is influenced by the other properties that we choose to measure. The likelihood of manifesting certain values is influenced by the other properties that we choose to measure. And the Koch-and-Specker theorem is another thing lurking in the background, which I don't think, and we're not going to say any more about it tonight, I don't think has been given enough attention in terms of what it's telling us about the way in which reality is structured. So very quickly, I've really talked a bit too long. If I would draw any conclusions about this, personally, here are the conclusions I would draw. If any 2 objects become entangled, then going forwards from there, if you do stuff to one, it will have influence on the other. That's what entanglement means. Even though no information could get from one to the other in the time frame. And therefore, and this quantum effect is real, experimentally verified, and actually, as we may well hear more about tomorrow, technologically, really quite useful. But further than that, it suggests, I see it personally, be interested to hear other views, it's strong evidence to suggest that there is an implicate layer to reality, which helps govern what goes on in the explicate layer. The implicate layer is not limited in the same sense that the explicate layer is, and it's those influences going on at that level, which is actually correlating what happens between Alice and Bob. I also personally happen to think that this notion of entanglement undermines one of the principal assumptions that goes into much science, the idea of reductionism, the idea that wholes can be divided into parts and that the whole can be understood simply in terms of the properties of the parts, and that those properties of the parts are not influenced by the whole. For me, entanglement drives a coach and horses through that, at least for quantum systems. And I think finally, some of us might be interested to see these 2 quotes from 2 of the founding fathers, Werner Heisenberg and Erwin Schrödinger, 2 of the most philosophically sophisticated of the founding fathers of quantum theory, and some of the views that they drew from that. My apologies for taking too long. I've really spoken for about 10, 12 minutes longer than I ought to. And I do hope that doesn't curtail the conversation, but thank you very much indeed for giving me your time.
Amazing. Thank you so much, Jonathan. Your presentation was so clear, and I bet it has helped many of us that don't have a physics background to tackle the weeks ahead. So thank you very much. And of course, I love the little memes on the corner of your slides. Quite funny. So yes.
Quite funny. Quite funny.
The timing was off. But yeah, so I'd like to obviously encourage questions now. If you'd like to ask a question, you can use the raise your hand function on Zoom under reactions at the bottom of your screen, or you can always write your questions in the chat. I think given the nature of this presentation, I'd like to encourage first people who don't have a physics background, if you have any clarifying questions, for example, and then later on we can move on to the more heady ones. I can see Pam has her hand up. Please come in.
Thank you.
Hi.
Jonathan, hi. That was just utterly amazing. I'm not a physicist, I'm a painter. And I've been trying to get my head around all kinds of things for a long, long, long time. Hence, I got very involved with David Bohm's work and understood quite a lot because of the variables that you're talking about.
I'm so sorry to cut you off. The sound broke up for me then. I didn't quite catch what you said. I do beg your pardon. Would you mind?
Of course. Quickly to explain, I'm a painter and I became very interested in quantum physics, arrived at David Bohm and learned a lot through his work. And talking about hidden variables and entanglement, and your beautiful slides and wonderful talk has helped me a lot. But the basis of it all is, am I right? If everything exists in the implicate order, then therefore,
I'm so sorry. I got the therefore, and then the sound. I got the therefore, and then the sound froze. Did it freeze for everybody? Is it just me?
Well, I'm probably making an awful mess of this.
No. I'm going to switch my video off in case having that on is influencing my Wi-Fi. So I do apologize. I got to the therefore, and then.
I apologize, but my understanding of the implicate order is that everything exists within it. And therefore, if that's true, entanglement, hidden variables, non-locality, influencing everything within the implicate order happens naturally and therefore affects what is explicated in the explicate order. Am I vanishing up my own bum here, or do I understand from what you're saying that all these quantum experiments are already within the implicate order, and this is just another way of expressing them? Sorry, I'll leave it there.
I would phrase it slightly different, but my view is that broadly, I agree with what you're saying. I would say that things don't exist in the implicate order. The things that we come across in our daily life very much exist in the explicate order.
Yeah, I
should the nature of their existence and the business that goes on at the explicate layer is very much influenced by business that's going on at the implicate layer.
Yeah, so the hidden
and so I would phrase it that way. Yeah. And I would pick up, and Basil and Bernard may well follow me in this, or may well not. I would pick up further on the notion of processes, and I would say that there are processes going on at the explicate layer which have embedded within them perhaps processes that are going on at the implicate layer, and so therefore there is some degree of autonomy that the processes can, to some extent, go on autonomously at the explicate layer. But there's going to be some processes that are influenced more by what's going on at the implicate layer. The only other thing I would say is, regard to talking about hidden variables, it may well be that there is some hidden variable theory lurking in our future somewhere, but we don't know what it is. We don't know where to look. We've got no way to speculate as to what it might be. So I don't think personally, I don't think in terms of hidden variable theories. I think that's a dead topic. It is simply that quantum theory, at least to some level, appears to be an accurate description of nature, and that is pointing me in my philosophical quest towards the existence of a layered reality, whereby we have, as it were, nested processes influencing each other. I don't know if that helps anybody, but that's the way I kind of think about it.
But we could say that the implicate order influences the explicate order, couldn't we?
I'm not an expert on this, I have to say, because I'm not an expert on David Bohm's philosophy here. I would think, Basil, help me out here, David would say the explicate order arises out of the implicate more.
Okay.
Yes, that's right, Jonathan. But I think I would like to wait until I have my turn next week, and then you can ask these questions, and then I can provide hopefully some answers to them. Because at the moment, Jonathan's very kindly, very nicely given the orthodox view.
Yeah.
And David Bohm questions the orthodox view, and I've continued questioning the orthodox view. So I'm going to look at it in a different way and then see what the reaction of the audience is going to be. But please, other people want to ask questions.
Thank you.
Thank you, Pam. And yeah, as Basil said, more to come next week. Next, we'll invite in Richard. Hi, Richard.
Hello, James. Well, thank you immensely, Jonathan, for the talk. As a complete idiot as far as science is concerned, and a victim of what in Cambridge we used to call the two cultures. When I was a student.
Snow rides again.
Yeah, I'm on the art side. I'm a poet. So I'm going to ask you perhaps this will be very cheeky, but a poetico, metaphysico, philosophico question. And that is that you ended up your brilliant slides with something that mentioned Indian philosophy. Yeah, I didn't quite catch it because it happened a bit fast. And all along, I was the whole while you were talking, I was thinking of the Indian myth, or if you like, image, composite image of Indra's web, whereby every point in the universe is connected with every other. So the universe consists, if it were to consist of points, if it could be infinitely multipliable into infinite points, then each point would be connected with every other. And that, I think, is also, from my point of view, a philosophical and even a religious point of view. It's certainly a poetic point of view, because I think most poets will have the assumption that in the very act of creating metaphor, things, as we call them, phenomena, are linked. And this would also connect with some work I've done. I've written a book-length poem based on the I Ching. And a number of scholars who've written about the I Ching have talked about the fact that or the idea that it's based, as all poetic writing is based, on what they call correspondent cosmos building, or if you like, basic connectivity. So that sums up, that was a bit long as a preamble, but my question is this: does everything in the universe connect? Is everything in the universe entangled with everything else? So it ends up with a sort of child's question, I suppose.
Well, I think I would construct an answer kind of partly as a bit of a cop-out by saying that that's kind of exactly what the whole point of these next few weeks is going to be about, that we're going to be exploring various aspects of that possibility. So that's one thing I would say. The other thing I would say is that if one accepts, as I do, obviously, well, not obviously, but as I do, the Big Bang theory of the creation of the universe, then in essence, at some point, all particles must have interacted with one another earlier in the universe. The question, though, is to what extent can that entanglement be maintained? Does something else break it at some point? So it's clear that early in the universe, the particles would almost certainly be entangled with one another. Whether that flows through to right now is a bit more of an open question. The other thing is that all of these conversations that we've been having and all of these illustrations and discussions talk about quantum theory, whereas actually there is also quantum field theory, and that goes down another level. And in there, we're saying that each individual electron is actually manifest out of the underlying quantum field of electrons. And therefore, all electrons are entangled with one another simply because they are all aspects of the one underlying field. And there'll be a field for photons and a field for all the other different particles. And that every time you come across a photon or an electron, it's actually, I think of it picturesquely as being like a bit of a ruck in a carpet. There's a little bit of a ruck in a carpet. If you try and smooth the carpet out, the ruck pops up somewhere else. The electrons manifest themselves out of the underlying quantum field. And I'm sure, Basil is working on aspects of this which go even I suspect, even further down than the underlying quantum field. So I think the answer to your question, I would phrase personally, is, yeah, I'm attracted to that notion philosophically. I think working at that philosophically opens up various possibilities for what we might or might not see in nature. I'm not sure at this point the science absolutely backs it. And therefore, I'm kind of chiseling my way out of the science towards something else, if I can phrase it that way. Does that answer your question at all?
Well, it certainly gives me a lot of lines to think of along. And I'd just like to thank you very much indeed for illuminating things that I just didn't understand. Superb.
Well, I'm
Thank you
very
so
glad
much.
to have,
Absolutely
very glad to have contributed a little way if I could.
Thank you very much indeed.
And again, I apologize for having my camera switched off, but the sound's been much better and much less broken up since I did that.
Well, thank you so much, Richard, for coming in. Always great to see you. Next, I'd like to invite Carol to come in.
Oh, you got an automatic unmute. Hi, I was trying to unmute myself. I've been, sort of exposed to the ideas of the implicate order and the explicate order for a long time. But listening to the talk, it suddenly occurred to me that at some funny level, I had no idea what the distinction really was. That it did seem like a continuity, and I'm wondering how you or physicists in general distinguish between the two. Is it just based on what we can see or what we can measure, or is there something? Is there a real boundary between those two concepts or worlds or ways of looking?
I can certainly give you my own personal approach to this, but I have to confess, and I confess this on bended knee and somewhat humbly in this audience, that I'm by no means an expert on David Bohm's thinking, and I really didn't want to confess this, but I'm going to. I haven't read Wholeness and the Implicate Order. I've started to read it twice and various things stop me from finishing it. So I need to confess that right now. Basil is looking at me with horror in his eyes. I can tell. I promise I'll try again. I'm very much looking forward to Basil illuminating this a bit further. All I will say is in my personal terms, I like the terminology. Whether I'm using it the way that David Bohm intended, I don't know. I suspect possibly not. My apologies. For me...
Oh, okay. No, go ahead, because...
This thing called the amplitude, we use it every day to calculate things to do with quantum mechanics. But there is no really good opinion as to what, there's no really consensus opinion as to what it actually is. Some people think it's just simply a calculational tool. I think there is something a lot more to it than that. As I mentioned briefly in passing, it uses a type of mathematics called complex numbers. And these are numbers that we don't see in what I might arguably call the real world, but okay, say the explicate order. I can count 1, 2, 3 objects. I can't count I objects or 3 I objects, whatever. The fact that quantum theory requires the use of this very specific form of mathematics is quite singular to me. And to me, that is a signal that we might need to expand our definition of what we call real. And I'm not sort of launching out on my own in this. I'm listening to advice given in writings, obviously, by people like Werner Heisenberg, who said we need to embrace Aristotle's idea of potentia. We need to embrace the idea that the world is influenced by potentials that might happen. And so I think this amplitude, this quantum thing described by complex numbers is actually real. It's a real thing, but it's a real thing that we can't touch and we can't measure. We need to extend our definition of reality to include it. And I would say there is this layer of reality underneath what we can touch and feel and see and smell that we can't directly interact with, but it is in there that the quantum amplitude has a real existence in its own terms, and it influences what goes on. And so for me, I use the term implicate simply to refer to this layer underneath the explicate, the layer of reality that we walk around and sleep and drink and eat in, that actually influences the processes going on. I suspect that is not, I suspect that is not entirely congruent with what David intended, but that's why I use the terminology.
But I think you're getting at what I'm, I don't have the mathematical background, and as my late partner used to point out, that that left me pretty crippled, but I'm still fascinated. And yeah, it does sound like you're kind of pointing at, like, the mathematics is pointing towards something. It isn't necessarily the thing itself, but it's pointing at the distinction between what in the way we're embodied we are able to perceive either directly or with the tools we can build, and what we have to go beyond in a kind of an abstract way to make sense of what it is we're seeing when we investigate it closely. So it's very interesting, and I'll be really interested to hear what Basil has to say about it too. But thank you.
I think I would summarize just very quickly. I think I would summarize by saying, I kind of feel like I'm waving my hands around in the air and trying to make an argument. In fact, if you could see me, I'm waving my hands around. But I think this notion of an underlying layer to reality is a kind of the right direction to wave my hands in.
Mm-hmm. Yeah, and I mean, I've always sort of thought of it like that, but it's occurred to me that that's a kind of a shortcut that can easily become very misleading, in the way that people think of, God in heaven and us down here. I mean, and I don't, I think we're looking at something a lot more, kind of, real. Really, it's like what you said. It expands the definition of what real might mean. So, yeah.
Again, if I was going to use terminology, then I'm not an expert on Aristotle's philosophy, but this notion of potentia, this notion of objective possibilities, I think is I find it a nice way to think about quantum theory.
Okay. No, yeah. Thank you.
Thank you, Carol. Jonathan, are you happy to take one more question?
I'm happy to go on as long as people want to go on, James, but I don't want to entomb them here.
Sure.
I'm conscious that I overspoke, so I feel like I owe people at least 10 minutes.
Well, let's take this last question from Alan.
Jonathan, thank you. That was a brilliantly clear presentation. It was fantastic.
Alan, you're very flattering. Thank you.
Well, I've got two sort of, I think, maybe impossible questions on your final thoughts. So please feel free to be very brief. The first one is, am I right in thinking that nothing that you've talked about actually addresses qualities, but everything that we've been talking about so far in quantum physics is about quantities? And so if we take qualities like beauty or experiencing the color green, I don't know whether they reside in the explicate order or the implicate order, but at least so far, it's not something we've been addressing. That's one question, qualities.
I think I can answer that straight away. Yeah, absolutely. We have not addressed that at all.
Okay, thank you. Then the other question was, I saw in the equations T for time.
Yes.
I'm just wondering, in terms of the presentation, what it tells us about time, and also just remembering Bernard Carr, and I believe his theories about there being more than one dimension of time. In terms of entanglement, does it tell us anything about time?
I don't think it does. Again, the conversations that we've had and the equations that I've shown are all in, what I might call standard quantum theory. And therefore, time is something that just goes on in the background, is ticking away in the background, and is helping to influence the values of certain things as time progresses, that they evolve through time. And the way in which amplitudes evolve through time is very, very, very well described by quantum theory. Our equations tell us exactly, if we start off with this certain amplitude and we wait, it will have evolved into something else. And we can calculate exactly what that something is. But then we take a measurement. Sorry, if you wouldn't mind, I'm trying to crystallize my thoughts. We then take a measurement, and that collapses the amplitude into one of the possibilities. That is not described by the equations in the same way. The nice progressive evolution of the amplitude and the sharp instantaneous change into one of the possibilities being manifest. That falls outside of the standard description of quantum mechanics. It's like a bolted on assumption in a way. Now, quantum field theory is the attempt to merge, the successful attempt to merge quantum theory with relativity, and therefore space and time start to become on a more equal footing. And indeed, we start to then talk about possibilities for quantum gravity and that sort of thing, where space and time must take a more active role, but we really don't know where the hell we're going with that. And then all bets are off almost with that. We need, by an awful long way from being an expert in this area, there are far more expert people in the room than me, but it seems to me that we need a whole new set of concepts to deal with this. And those concepts are going to have to tackle space and time in a more fundamental way than we are dealing with them at the moment. And indeed, Bernard's got models, as you say, for progressive time and hyperdimensionality along those lines. So I think the answer is, if we're just sitting in the weird enough as it is layer of the standard quantum theory that you get in undergraduate level, then time is just something ticking on in the background.
That's really interesting. Just the sense, at least in terms of what we've been covering today, our common sense view of time is good enough, albeit there's this collapse that happens that's instantaneous.
Can I just
help me out?
Well, I just comment briefly in response to Alan's point. I don't think anything that we've heard about today hints at higher levels of time, but there are some interpretations of quantum theory which do. I mean, for example, the Aronoff and colleagues have a sort of two-time interpretation of quantum theory. And the general invocation of higher dimensions, I do think personally that when we're going to have a final theory which is going to amalgamate, if you like, relativity theory and quantum theory, I think it's very likely that will involve higher dimensions. And indeed, even if you read Bohm's Implicate Order, that he also hints at that even in that book, that you may need a higher dimensional interpretation. In general, the problem of time is that there is a problem of passing time as opposed to normal relativistic time. In other words, the time of consciousness. And the point is, there is no room for the time of consciousness within relativity theory, because you have the block universe. And some people have said, well, maybe the time of consciousness has some relationship to the time of the collapse of the wave function, which suggests that maybe that problem will be solved within quantum theory. But even the standard picture of quantum theory doesn't resolve that problem of the passage of time. In other words, getting consciousness into the picture. But as I say, I think there may be some interpretation, some deep interpretation of quantum theory, which would allow a higher dimension of time. I would be very interested whether Basil has any comment on that, because I'm not sure even within Basil's approach whether that's particularly attractive.
Well, I've actually published a paper actually having two types of time.
Oh, great.
It was published in a rather an odd conference, which probably hasn't got into the popular press, but I've certainly speculated about different types of time. But the trouble is, it comes in through the mathematics, and it's so difficult to get the ideas across to people who do not have a feeling for mathematics. This is always my stumbling block. I tried to bring in analogies, metaphors, but I always feel something gets lost in the metaphor. It's a bit like waving one's arms, trying to get something which it has a very definite form in the mathematics. But when you try to get it across in terms of some imagery, the imagery always gets in the way. And it's very difficult to say where it's actually coming from. That's why I can't talk without having equations in front of me, because they are telling me what I should be looking at. But of course, that's not helpful to people who are come from the other side of the divide, in the two cultures divide. But in fact, David always used to say to me, we are really poets, Basil, in our science. We should adapt more the poetic view of science if we want to progress from where we are now. In other words, it's the mechanical view that sticks us in a particular paradigm. And what we haven't got the courage to actually go past the boundaries of that paradigm, because our colleagues wouldn't like us, you see. But now I've retired, I couldn't care less. And I feel this is one of the big problems. We have to break down the barriers.
Well, Basil, they say that maths is the language of God, so maybe that's why it's hard to understand God as well.
I would just say it's a language. It's a language we have to learn.
Indeed.
I mean, when I said earlier on, I only have two languages. Actually, I have three: English, maths, and gibberish.
Basil, could I ask you, I haven't seen this paper you referred to where you talk about two times. So,
oh dear,
could I ask you? Could I send you could you send me the reference in an email afterwards?
Yes, okay.
And maybe I can just add that Basil mentioned poetry, and I guess that brings in qualities.
Yes, that begins, but it's very difficult through the mathematics to bring in qualities.
Yeah.
That's where the difficulty comes in.
All I would say, Alan,
could I just add here that what we need physicists and poets. If we can get together, then perhaps we can meet somewhere in the middle. Metaphysics and politics as well.
I know quite a nice restaurant. I know quite a nice restaurant bar area in a little village in Italy.
Yeah, I think doesn't it begin with P?
Something like that. Something like that. Some obscure guy founded something somewhere. I can't remember.
Yeah.
Alan, you and I have had plenty of, slightly sober conversations about this in the past, I know, but all I would say in regard to the qualities thing is that, again, I come back to this notion I have of layers of reality, and the possibility there might exist a mental layer in there, although I don't think they are layered in like a lasagna. I think there's a gradation to them, and I think that's where we might talk about exploring qualities, because again, I don't want to divert the conversation in that direction, but there's something specific about mathematics, that's something fishy is going on with mathematics as well, I think.
Yes, and you're saying it's only the complex numbers, but we've got the quaternions and we've got the octonions, and there's a whole zoo of different structures which we have not really mastered.
Yeah,
I'm talking now about the physicists and the theoretical physicists.
Yeah, I know. Yeah. And
I love the physics, poetry, Parry, Pete connection.
Yeah.
Yes.
Yeah.
And everybody's David, by the way.
James, bring some order to this, will you please, before we go off the deep end?
Well, thank you, Alan, for your question. You have raised a whole panel of people to answer it, so thank you so much for it. So I think unfortunately we do need to start wrapping up as it's 1:45. However, if you do want to keep going the conversation, I'm very happy to leave the room open for after everyone goes. If anyone has any follow-up questions or more discussion to have, if Jonathan, of course, is happy to stick around. So just to start to bring it to a close, Jonathan, do you have any last words or comments for us?
Only, very much appreciate the kind words of people who said they've enjoyed the talk. It very gratifying, and to say there are quite an array of very, very interesting people coming up over the next few weeks, and I hope to see everybody attending those, or as many of them as they can, as well.
Absolutely. Well, thank you so much, Jonathan, for today. It really was a clear presentation, a good grounding for everyone. And of course, it did set the tone to what's yet to come. And not only from you, but of course, from everyone here in the audience with your questions and comments. There's so many wonderful comments about your presentation, Jonathan. So thank you again.
I haven't actually had a chance to look at the chat. Is there a way of grabbing it and emailing me the content thereof?
We will. Yeah, we will.
I'll send it to you.
Cool. Thank you.
Great. Well, just before we go, just a quick housekeeping thing. So before this call, you may have seen an email from us inviting you to join Sutra, which is our online forum where everyone here is invited to join, audience and speakers. So it's a great way to keep the conversation going in the weekday break between sessions. And of course, it's a great way to share your thoughts and make connections with the rest of the Power Center community. I also like to invite you all to tomorrow's session where we have Professor Jose Latorre talking about quantum computing. So very much touching on the technological side that you mentioned earlier, Jonathan. And yes, I would like to wish you all a good evening, night, or day, depending on your time zone. If you have any questions or want to get in touch with us, you can do so by emailing eleanor@powercenter.com or otherwise directly on our website. There's a contact us section. But until then, thank you all again. Thank you so much, Jonathan, and we'll see you again soon here at the Power Center. Bye-bye.